Hi, I'm Robert O'Brien from O'Brien Guitars. I'm here in my shop with Trevor Gore from Australia. And Trevor literally wrote the book on modal tuning, guitar design, and build. He's got a 2-volume set. But he's here in my shop, and we're doing some talking here over the next week. We're giving a series of master classes. And I thought, well, shoot, let's turn the camera on and let's pick his brains a little bit. What do you think?
Well, let's do it.
All right.
There's not much brain to pick these days, but you're welcome to what you can find.
I've written down just a couple of questions. Of course, like I said, we're giving a master class here, a week of master classes. My brain is mush right now of all the materials that have been presented. But just a couple of things off the top of my head that came to mind were how to get more volume out of your guitar. And a lot of guys talk about that. I always want more volume, more volume. And I've always heard that, the more volume you get, you sacrifice tone and quality of tone, harmonic complexity, that kind of stuff. And along those lines, the thickness of the sides, will that do anything to contribute to the tone? Because I know Taurus went really thin on his sides. Mm-hmm. So can you elaborate on that subject a little bit?
Sure, Robbie. It's a complex story, so let's try and start at the beginning. And it really starts with how a sound wave travels across the top of the guitar. And you've got to think, well, how does that work? It actually moves as a bending wave. So almost like the ripple across the surface of a pond. Mm-hmm. And then when the ripple hits the boundaries of the pond, hits the shoreline, it bounces back and comes back and forms a standing wave. And you see these waves and they just go up and down like that. And due to some rather complex phenomenon, you only get the sound radiated from those standing waves. The travelling wave, until you get to about 4.5 kilohertz, doesn't actually transmit a whole load of sound. So it's only the standing waves that are reflected back into the top, right? Make the top go up and down like this. They're the only ones that produce the sound. So once you understand how the sound is radiated and reduced in the guitar, you can start thinking about, well, what do we need to do to make it sound louder?
Okay.
Well, clearly one of the things you've got to do is make sure that wave comes back at you.
Right.
If you let that wave travel across the top and down the sides and round the back, it's going to disappear and you're not going to get much sound out of it. So first up, you've got to make that wave come back at you. And what you need to do that is to put some pretty rigid boundary in the way of it. And you sort of think, well, okay, that's looking like a brick wall swimming pool compared with an inflatable paddling pool.
Right.
If you've got an inflatable paddling pool and the wave comes along, it's just going to push the sides around. Uh-huh. That's not going to do too much. But if you've got a solid, high mass structure there, when that wave comes along, it's just going to hit it and bounce straight back off it. So the first thing to think about is, well, let's think about how we do the linings of our guitar. If we make those big and heavy, when that wave comes along, it's just going to hit those linings, bounce straight back, and you're going to get a lot more efficiency out of your guitar.
Right.
So mass and stiffness in the linings is pretty much a good thing, unless you're building a flamenco blanco.
Let's do a timeout here. I don't mean to interrupt you, but I had trouble understanding this concept of mass and stiffness.
Right.
Okay. Stiff, good.
Yeah.
Mass, good.
Correct.
So what I had trouble understanding was, okay, let's say we use reverse kerfing, reverse lining, mm-hmm. but the type of species of wood, you want a dense wood.
Dense works well for that.
Even like an Indian rosewood, for example, would work well.
Yeah,
would
work well.
All right, so
but you've got to remember what type of guitar you're building. If you're building, say, a flamenco blanco, you want the exact opposite effect. As in a blanco, you want the sound to dissipate quickly because you don't want the notes to run into each other. So you build in entirely the opposite way from how you build a classical guitar. So on a flamenco blanco, you'd be looking for no discontinuity at the edge because you want the wave to travel around the top of the guitar and around the back and sort of dissipate to give you low sustain.
So the rubber swimming pool example applies here.
So a flamenco guitar would be like the rubber swimming pool.
Okay.
Whereas a classical guitar or a loud steel string guitar would be more like the in-ground swimming pool.
Right.
So that's one aspect of it. You want that wave to stay in the top so it can move the top up and down and push you out a lot of sound. Uh-huh. And the second aspect of that is that as that wave develops in the top, Some of you might be familiar with what we call cladding patterns. These are the patterns you get when you sprinkle tea leaves or dried herbs on the top of the guitar, shake it with a loudspeaker, and it produces a ring sort of effect on the guitar at the resonant frequencies of the top. Now, when you get a cladding pattern like that, where that line is in the top is a line where the wood is not moving. The area of wood inside that with the bridge on is moving up and down, and the area of the outside of that ring is also moving up and down, but in antiphase.
Right.
So you've got what we would technically call a concentric dipole.
Right.
Now, think about that. As the sound is radiating off those two surfaces, all the surface in the middle is radiating sound in one phase, and all the sound radiating from the horseshoe shape around the outside is radiating in antiphase to that.
And usually, what, half inch to an inch or so inside your...
bigger than that. So it can be as
inches.
much as a couple of inches inside.
Inside your perimeter.
Inside the perimeter, yeah. So, if you can move that node line outboard more towards the edge, you get more sound radiating in phase and less sound radiating in out of phase. And so you get a louder guitar.
More volume.
More volume. So you think, well, okay, that's cool. How do we do that?
Good question. That's part 2 of the video, right?
Yeah.
Oh.
Yeah. We'll see you next week. So that's a good question.
Okay.
Right? How do we do that? And the way we do that is to think about some more physics. And in there we got to go back to Sir Isaac Newton.
Okay.
He was a pretty smart guy, and he reckoned that any body that was moving, any material body that was moving, there needed to be some sort of equilibrium in momentum, action and reaction equal and opposite, and all that good stuff.
Right.
So if we have the part of the guitar top with the bridge on moving up and down, we have some mass, that's the bridge and the top in the middle of the guitar, that has mass, moving up and down with some sort of velocity. So that's mass m and velocity v, and momentum is 1 multiplied by the other. So momentum is mass times the velocity. If we have some momentum of some component of the guitar in the middle of the guitar moving down with momentum mv, there has to be some other part of the guitar moving around in antiphase to that with absolutely equal momentum in antiphase. So, which other part of the guitar is it? Well, it's the rest of the guitar, and it's in particular that part of the guitar outside of the node line, because we know we get a phase shift as we cross the node line, and that's moving in antiphase to the top. So we're having there a sort of concentric dipole radiator. To move that node line out, we need to consider that momentum equilibrium equation. So we want to make the outside move less, and we can do that by adding mass to it. Okay. So if we add mass to the side somewhere, we shift that mv equation around so that the sides move less, because there's more mass there. So mass times velocity of the sides, we've got more mass, so it moves less. Okay, what effect does that have? Well, the effect that has is that moves that node line outboard. Right. Yeah. So we've got more in-phase radiating surface and less out-of-phase radiating surface. So we've got one of those very, very rare occasions where we've got a double whammy win.
Win-win for everybody.
Win-win for everybody.
Life's good.
Yeah, and you don't see that often in any part of the world, never mind the guitars. And that, I found, works really well. We can add mass to the sides, and that moves the node line outboard. We get a bigger radiating area, therefore more sound radiated. And if we kept that wave going by having the stiffness around the outside of the guitar in the linings, we start getting a loud and efficient guitar.
Interesting. Now, one clarification, and I had trouble grasping this concept, was mass and stiffness. And we talked a little bit about laminated sides.
Yeah.
When you're laminating your sides, you're getting stiffness.
Yeah.
And perhaps you're getting mass.
Yeah.
Okay. Which is more preferable?
The mass.
The mass. We want the mass.
In this sort of situation. because it's the mass that's going to alter your momentum equilibrium,
Right.
not the stiffness.
Not the stiffness.
Yeah.
So it was kind of goes contrary to what I was always taught is stiff sides, more volume. Not necessarily the case. More mass, more volume.
And Torres wouldn't agree with you because he always used really thin sides.
That's correct.
So we've had this dichotomy for years of thin sides versus thick sides, and we still don't know why Torres use really thin sides. But if you use thick sides, the benefit is usually coming from, or the tonal benefits are usually coming from the mass effect rather than the stiffness effect. Of course, there are other benefits of using laminated sides, keeping the sides flat and the bendability and a whole stack of other things,
Right.
but they're not really acoustic related.
Very interesting. Folks, here's another question that I had for Trevor. When I first started building guitars, I used 4-back braces. Now, there were a couple of reasons for doing that. One of them was I was doing a lot of Brazilian rosewood guitars at that time, and the quality of Brazilian rosewood we had, or we have these days, is not quite what it was. So a lot of it was flat sawn. So I like that extra support, 4-back braces. Then I switched to using a lot of Indian rosewood, and I pulled out one of the braces. I didn't think I needed it structurally. Can you elaborate? Now, these are layman's terms, but I want Trevor to give us the scientific definition of what's happening by taking out one of those braces.
Yep. Okay, Robbie. Well, in my terms, in my language, there are 2 types of back. There are what we call live backs, and there are what we call non-live backs. And a live back is one that is light enough and springy enough so that it responds to the sound of the guitar. Now we have to remember how this thing is being driven. It's only being driven by the air pressure change inside the box of the guitar. So if that thing is big and heavy and stiff, it just ain't going to move, and you're going to non-live back.
Right.
So straight away that sort of limits your choices of wood to use. If you're using a really dense wood, almost certainly you're going to end up with a non-live back because it's just too heavy to move around.
Mm-hmm.
So we're looking at woods in the density range, say 500 kilograms per cubic meter up to about 800 kilograms per cubic meter. Outside that range, you're sort of pushing hard to make it work. So then you've got to design that panel to the right thickness for it to be flexible enough and light enough to be able to move. And then you've got to put a bracing system on it to both stabilise it and add more stiffness in the right place so it will vibrate where you want it to. So generally speaking, a non-live back is heavier and stiffer than a live back. So the design criteria for making a live back is you've got to make it flexible enough and light enough to be able to move and resonate at a frequency which is probably somewhere around 4 semitones higher than the top frequency.
Right.
And when I'm talking about these 2 frequencies here, I'm talking about frequency peaks and the frequency response curve, where we measure the top frequency as the second peak in the frequency response curve, which we call the T112, and the back we sort of rather lazily call the T113, and the separation between those 2 peaks needs to be around 4 semitones. And if you can do that and get those 2 peaks, you've got a live back guitar. So what's the difference, you might ask, between the sound of a live back and the sound of a non-live back?
Right.
And having a guitar with a live back and a flexible back introduces more peaks into the frequency response curve, and more peaks in the frequency response curve equates to a more interesting sort of a sound.
Harmonic complexity.
More harmonic complexity, okay. Absolutely right. So in very crude terms, we can say a live back gives you tone, mm-hmm. and a non-live back gives you volume. And the reason why the non-live back gives you volume, because obviously if you're moving the back around, you're taking some sort of energy out of the system that's not being radiated towards the audience's sound.
Right.
So if you're subtracting energy out of the system, you're going to get less of it out front.
Makes sense.
Yeah. So very simply, a live back gives you tone, and non-live back gives you volume.
Perfect. There's your answer, guys. Thank you, Trevor.
No worries, Robbie.